right, thank you very much. In the interest of time, I'm going to introduce Kyle Goodrick, who is speaking next on electrified transportation optimization with CVXPY.
Excellent. Well, hello everyone. I'm Kyle Goodrick. I'm very excited to be here. I am a senior power systems research engineer for Aspire, which is a university, like a lab that's NSF-funded engineering research center based out of Utah State University. And we do all kinds of electrified transportation research. So yes, very excited to be here. I personally have been a CVXPY user since grad school. Did a little bit there, and then I've been using it pretty much every day for the last 2 years or so. And then I contributed a interface for the Cosmo solver. So yeah, I really enjoy CVXPY, and I'm excited to talk to you guys about what I'm doing with it. So a little bit more about Aspire. We are this engineering research center, and we're doing work on all kinds of electrification. We're really interested in basically all the different modes of transit. So we're looking at heavy-duty trucking, personal vehicles, buses, trains, even somewhat part of aviation. And so we're looking at this whole spectrum of electrification and how that's going to transform society as we, lower the cost of moving people and goods. So a little bit about electrified transportation and why we want to do it. And the biggest advantage of this over more traditional transportation is that it's very cheap. That may be hard to believe with the California utility rates, but at least in Utah, electricity is very, very cheap. And we can get these huge reductions in cost over traditional vehicles for quarter the cost of gasoline. Just because that unit cost of fuel in an electrical form is just very, very cheap. But then, there are other benefits. The lower overall emissions, even in places like Utah where there's lots of coal on the grid still, we're looking at lower overall emissions. Great. And then in particular, we're really interested in these lower tailpipe emissions, less emissions where people live. In Utah, even when we have that coal, it's way out of the city. So it's less impact on human health. But the vehicles, those are always where people are going to be. So eliminating those tailpipe emissions is huge. And then in Utah, we're very concerned about the brown cloud. You may not believe it, but there is, in fact, the city behind all of that pollution. You can see the downtown buildings are right there. Those are not clouds. It is not fog, but it's smog from the inversion layer, which traps all of the pollution in the valley until the next storm comes in. So that is one of the big reasons why Utah is so interested in these modes of transit that reduce emissions. Okay, so EVs are great, but there are also some challenges associated with them, or as I like to look at it, there are opportunities for optimization and ways to really improve that. The functionality. And so the biggest one is that they have these very high peak demands. You can see in this top upper right corner, the demand from a hypothetical regional train. And so it comes, in the morning every 15 minutes or so. Occasionally you even get 2 trains are coming at the same time. In Utah, we have this unique situation where the regional train runs on shared lines. They can't put catenary lines in everywhere, so they have to do some pulse charging when they get to stations. And when they do that, they can draw up to 8 megawatts when both come in from both directions at the same time. And so that's several thousand homes, but they're only there for a minute or so. So this huge load that only happens every now and then, and it's very straining because you have to build infrastructure for all that, but then most of the time it's not being used, especially when you start looking at overnight weekends when the trains running at all. And even for more traditional applications, like we have this remote site, which is basically out in the desert in Utah. People are still driving there, but there's not a lot of electrical infrastructure. They still have their personal vehicles that they want to charge. These sites can draw, up to nearly a megawatt when the vehicles, multiple vehicles arrive and during a busy period. But a lot of time not being used. This site over the course of the year has like a 3% utilization, so it's really, really quite low utilization. So that can be very expensive for those early adopters. But the good news with all this, that EVs are a very unique load. They have a lot of great properties that allow us to work within those limitations. One of the big ones is multimodal integration. We can co-locate multiple transportation modes that have different duty cycles and operating modes, so that we can interleave their loads. We can combine the flexibility of the vehicles. They can shift, like unlike pretty much everything else that you connect to the grid. If you want to do something with that energy, you have to pull it from the grid at the exact moment you want to do the thing. EVs are the complete opposite. You plug the car in when you're not using it, so that you can use the energy later when you're not connected to the grid. So you have a lot of control over, when exactly you're pulling from the grid. That can be both while you're plugged in, or you can even think about changing the operating mode of your use of transportation to add to that flexibility. These high intermittent peaks also give us the opportunity to use on-site storage to minimize the need for grid infrastructure. And we can do all of this, together with grid coordination, so that, there's a lot of underutilized capacity on the grid today. Most of the time, we're only using about half of what is installed. But we have to build for that peak. And because these EVs can be so controllable, we can coordinate with that existing underutilized infrastructure to really lower the cost of providing energy for EVs, and then ultimately for all users of energy. We can get more energy onto the same amount of infrastructure, the unit costs are going to go down. So that can change the way that society interacts with energy. And so I'm showing here on the bottom kind of an example of this multimodal site, where we have that front runner come in. It starts pulling a huge amount of demand for only a minute or so. And what you can see is that that red line is the train. There's also hydrogen production at this site in yellow. There are buses that are also charging at the same site. And you can see when the train pulls in, the hydrogen production stops. The buses actually start providing some of that energy temporarily in their batteries through the train. And you can see that it's the light blue line that's right behind the green line that's showing the grid capacity. That light blue line is the power coming from the grid. Even though we have this huge spike in demand from the train, we're actually getting constant loading to the grid. So really high utilization of the assets that we have. And so this is great. But then the question that leads to is, like, how do we know what these energy flows are? What's the right optimal choice? How much battery do we need to realize that? How much interconnection do we need to the grid? And then how do we balance the cost of all of these different infrastructure that we need to build over the utility rates for the whole lifetime of the system? And so that is a great application of linear programming and convex optimization. We have this, I'm showing here an example, a simplified model of the system. We have the grid that can provide or take energy from a central bus. There's a battery that can do the same, and then different loads that can all take or receive energy from this central summing node. And then we have a linear constraint that all the energy going in has to equal the energy going out. We can calculate demand charges and energy charges. We can look at utility rates, or we can look at market prices. We need to keep track of the energy that's stored in the battery, and we have all of these linear costs and constraints, and we want to minimize the cost of the infrastructure we're installing, the lifetime energy purchases, all those things meeting the demands of the vehicles, the physical constraints of the system, and taking advantage of any existing infrastructure that we have. Okay, so I'll show quickly two case studies. One here is this Wasatch Front electrification. So this is Salt Lake City, which is where about 80% of the people in Utah live, and basically took a week of data from the public transit buses. We assume they're all electrified. This is a different LP, so I won't spend too much time talking about it, but it figures out, where they should charge. And then we did the same thing for 30,000 trucks, and then we added in the train as well. And then we figured out, where the peak demands were going to be. So that separate tool gives us the demand for each of these sites, when it's going to happen. And then the tool that I'm talking about today is going to make those decisions about how much energy storage do we need, how much grid interconnection do we need, how much downstream or upstream substation upgrades are we going to need, and then answer questions that the local stakeholders have, like how is this going to impact the small municipal utilities in the state that don't have these huge infrastructure to absorb these massive loads. So you can see kind of the impacts of this tool looks at taking advantage of some grid knowledge and not taking advantage of it, how that impacts the planning process. So that is all there. And then I'll show another output of the tool. And so this is showing a week of energy demand from the flows in the system, 15-second intervals for the whole week. We can see that the trains are coming in often. The battery is taking over for a lot of that load, and the buses are doing all kinds of stuff. And then the critical thing is that yellow grid demand, it's basically constant except during the peak demand periods when it drops off almost entirely. So we're really coordinating with the grid. The big purple line is the existing capacity, using that capacity and avoiding those times when it gets very low. And so we can do all this with the linear program, which is very interesting. And then we have one more example with a rural fast charging site. So Utah is a very remote place. There's lots of places where there's basically no grid infrastructure. But there are still people there with EVs because there's tons of tourism. And these, the limited grid infrastructure there can be constraining for EVs, especially with NEVI that can require like up to 720 kilowatts of peak demand from these sites. And if we have to upgrade a substation for that, which is the case of this example, the site's not viable anymore. It's millions of dollars for a site that gets 3% utilization. And so we can use this tool to figure out how we can afford that substation upgrade. Here's kind of a plot showing the energy, and then critically, what you can see is that we lower the peak demand here to 184 kilowatts. We only need 250 kilowatts of grid interconnect. The grid peak demand is a 15-minute average. That's the way the utility calculates their peak demand charges. 600 kilowatt hours of storage and a total unit cost of 15 kilowatt hour that's well within the rates that people are accustomed to paying for utility charging. And then this can all be solved formulated with CVXPY in a really great way. We can keep track of the energy storage. You can see here that we're very actively using the battery to avoid those grid upgrades, the peak demand charges that the utility offers, and then it's very flexible. CVXPY makes it very easy to be flexible, and so you can put in market rates, all kinds of stuff, not just those utility tariffs. Very, very useful. And then just to wrap things up, CVXPY makes doing this extremely pleasant. It would be super difficult to do this, formulating just like one matrix. And so being able to model every energy system as an object, they all have properties that are returning, expressions that can have variables or parameters. Sometimes they can return one or the other depending on what kind of thing you're looking at. So CVXPY makes it really, really great. Checking DPP or DCP for each of these sub-expressions can help if you accidentally make a non-linear expression. Is really helpful to do all the debugging of the system. So it's great. I really enjoy it. I really appreciate all the work that you guys have put into making the tool. It makes my job possible, and I think it's we're gonna change the world with it. So I really appreciate it.